Well, hello. I'd like to welcome everyone to this Epoxy Technology Incorporated webinar. My name is Rich and I'm a Senior Manager with IHS, and I'd like to review just a few housekeeping items with you before we begin. Let's take a moment to familiarize ourselves with the operation of the user interface for today's webinar. Now, the large window that you're currently viewing with the heading Epoxy Technology Incorporated Presentation in the upper left, that's the primary window for today's webinar. You should be seeing the welcome slide there right now. Now, just to the right of that main presentation window, you'll see the speaker's bio window, and that contains background information on today's presenter. Okay, now just below that there's a Q&A window, and at any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will then be placed in the queue for our speaker to address when we get to that Q&A session. Now, if you look to the bottom of your screen, you'll see additional buttons to enhance your webinar experience. To see what a particular button does, just hover your mouse pointer over it, and a tooltip will appear with a description of that button's function. Okay, now to get this webinar started, here's your International Technical Applications Engineer, Brian Bruce. Brian?
And thank you very much. Yes, hi, I'm Brian Bruce, and I will be presenting today Epoxy Technologies, Epoxy UV cure optimization, and UV hybrids. Today's presentation is going to be broken down into two parts. The first is going to be going over epoxy UVs and UV adhesives. The second will be going over UV hybrid systems, a brand new technology. First of all, in the UV systems, we're going to be going over the difference between cationic UV epoxy and UV free radical acrylate systems. Cationic UVs are an epoxy resin that is polymerized with a light-initiated photoinitiator. Cations are generated by light or by heat, typically by light activation or UV activation. You can see a cure mechanism here, or at least the mechanism for how the photoinitiator is activated. In this mechanism, a UV light comes in and dissociates the photoinitiator to create a strong acid. That acid is the cation and is an intermediate species that's going to generate a living polymer within the epoxy resin. Once the photoinitiator is activated with a UV cationic epoxy, the polymerization reaction goes forward. The acid actually promotes the ring opening. You can see in the top step the addition reaction of that acid. In the next step, you can see the ring opening of the epoxy group and an addition of a new monomer, an R group. You can see the ROH that's coming in. That's actually an additional entire monomer. In the third reaction, you can see the acid actually leaving and being replaced or substituted with that new monomer, that second monomer. You can see in this the acid is fully regenerated, so this is a truly catalytic reaction. Now, this process will continue forward until completion, and that will create a large polymer network or a polymerization. You can see that this reaction is multiple steps. This actually leads to a slower reaction overall, as all the monomers have to react to dimers, those dimers to trimers, those trimers to oligomers, and it's limited by the mobility of these large molecules. Because this reaction does take some time, properties can develop over a 24-hour period, properties such as strength and reliability. So testing is best done after a 24-hour period, after your irradiation. Cationic epoxies have a wide array of benefits. First and foremost, they are epoxy-based, meaning they have epoxy backbones. Those epoxy backbones lead to much longer-term reliability than your standard acrylate systems. They produce better 85-85 resistance, better thermal cycling, and much lower shrinkage. With acrylate systems, average shrinkage tends to be about 10 to 15%. In most epoxies, that's going to be about 1 to 5%. Much lower shrinkage leads to much lower internal stress. That's going to actually increase your adhesion, decrease shrinkage, increase alignment, all great things. Additionally, cationic epoxies are not subject to oxygen inhibition. With free radicals, the free radical that actually does the curing can be quenched by oxygen in the environment. That doesn't happen with cationic UVs. Additionally, cationic UV epoxy is capable of dark curing in some cases. Dark curing is the epoxy polymerizing in areas that don't receive full UV illumination. Now, this is very geometry dependent, but many cationic epoxies are actually enhanced, or their depth of cure is increased with a thermal post-cure. Many of them are thermally post-curable, meaning that they can actually see heat in an oven and increase their degree of conversion, have increased physical properties, and increased reliability. Additionally, there are some photoinitiators that can be used in cationic UV epoxies that are truly dual curable, meaning in total shadow areas, after they've been UV illuminated, they can actually be thermally post-cured to achieve pretty complete cures, even in parts that receive no light. These usually require thermal cures up to about 120 Celsius and are really only capable of occurring with a couple of select formulations. But it's absolutely possible and only possible with cationic systems. Cationic UVs do have some drawbacks. For example, they are sensitive to moisture. Too much moisture in the environment can absolutely negatively affect your cure quality. And we've actually seen that dry air purging can substantially increase cure speeds. Additionally, cationic systems are sensitive to basic materials and basic substrates. For example, a urethane would be very difficult to bond to because of the actual amine within the urethane is going to neutralize the photoinitiators in the cationic UV system. It's going to lead to poor curing, it's going to lead to poor adhesion, and can actually give a wrinkle texture. Additionally, the acidic species that's generated can actually promote corrosion. Now, this is very rare. It's very uncommon that I see this. That said, it is absolutely possible and something to be aware of, to watch out for. Additionally, and one of the biggest concerns we run into, is cationic UVs do cure more slowly than acrylate systems. Acrylate systems tend to cure in 2 to 20 seconds, whereas epoxy UV systems take more like a minute to 2 minutes. That said, epoxy UV systems can have their cure speeds increase substantially with warming. That would be that thermal post-cure that we discussed, or downstream thermal processing. That's also going to increase the rate of reaction. So that's your UV cationic systems. Now over to the UV free radical acrylates. UV free radicals, most commonly known as acrylate systems, are very fast curing UVs. You can see here the mechanism for how they're actually curing. UV light comes in and creates a free radical that starts a chain reaction that polymerizes or propagates down the chain of monomers, almost like a zipper. Once that free radical has found all the monomers that it can get to, eventually it will be quenched by oxygen in the environment. Once the oxygen reacts with that photoinitiator, with that free radical, the reaction process is done. The benefits of free radical systems, they're very, very fast. They take anywhere from 2 to 20 seconds. Some a little bit longer, but most are in that couple of seconds range. Additionally, they have very good through cure, meaning depth of cure. Typically, these can be on the scale of a couple of millimeters in depth, depending on your lamp selection and photoinitiators used. Additionally, free radical systems are typically very optically clear and non-yellowing. This, of course, does depend on the photoinitiator and monomer used, but they are typically quite clear. From a formulation perspective, free radical acrylates, there are many raw materials out there, many monomers, many hardeners, many photoinitiators, and all of those lead to a lot of variety in terms of what is formulatable. Moreover, they are not sensitive to moisture or basic materials like UV cationic systems. Additionally, no thermal curing is needed, and in fact, thermal post-cures do not affect the free radical systems. Once that light is turned off, the reaction is done. UV free radical systems do have some drawbacks as well. For example, they're prone to oxygen inhibition. Oxygen can interact with the photoinitiator, that free radical that's generated, and stop the polymerization from happening. This is actually noticeable when this happens too much in a tacky surface in the acrylate system. Additionally, you'll see poor physical properties. This happens when the free radical is terminated too early and is an insurmountable issue once it actually occurs. The only way to prevent this is by use of inert atmosphere, like nitrogen blanketing. We find this very common with customers doing free radical UV cures. Additionally, free radical UVs have very high levels of shrinkage. This can be one of their biggest drawbacks, in fact, that the shrinkage usually is about 10 to 15%, which in microelectronics and optoelectronics can absolutely change your alignment. Additionally, that can lead to lower overall adhesion due to high stress in the bond line. UV-free acrylates also are not very environmentally resistant. They tend to perform pretty poorly in things like damp heat testing, like 85 Celsius, 85% RH resistance testing. Additionally, they tend to have lower adhesion overall than your UV cationic systems. Moreover, free radical systems are not shadow curable at all. The light has to hit the full bond line in order to cure it. Finally, free radical UV systems tend to be quite volatile, meaning that once you cure them, they'll have an unpleasant odor. This can actually be potentially hazardous toxins that are being released from the monomer. They tend to be very low-weight molecules, and it's definitely something you're going to want to watch out for, and you'll very quickly smell. So those are your two basic types of UV systems. Now, how to cure them. Onto the lamp section. There are two main types of lamps. The first is the metal halide or doped mercury type lamps. The second is the LED type. Now those can be further divided into flood cures and spot cures. Flood cures being a large area of illumination versus spot cures being a very tight area of illumination. And we're going to go into more detail about all of these varieties shortly. So first, within the mercury lamps, there are many different types of mercury lamps, and we actually do have a preference here. There's the standard mercury, your H-type lamps. You can see from the spectrum on the left that they have a strong output all the way from 200 up to about 320 nanometers. Great for thin coatings, but they tend to be too strong in the 200 to 280-ish, that UVC range. That can actually skin over products. And we'll talk about intensity and the lower, stronger wavelengths a little bit further in the presentation. The next on the right side, you see the gallium, the V-type lamps. These have the strongest output in the 400 to 420 range and are not optimal for UV cures because they don't have those strong UV wavelength outputs. The 400 to 420 nanometer wavelengths actually don't really affect our typical photoinitiators. The other main type of mercury lamp is the iron-doped mercury, also known as the D or F type UV lamp. This is actually one of the ones we prefer. It has a very high output in the about 300 to right around 400 nanometer range. This one allows for good depth of cure, but also has an excellent overlap with many of the photoinitiators we use for our UV formulations. LEDs are quite different in their output spectrum. You can see here three of the most common LEDs, the 365 nanometer, the 395 nanometer, and the 455 nanometer. You can see in each of those graphs that the spectrum of output is very narrow. This can have some benefits in terms of depth of cure, but that very narrow spectrum does not fully activate the photoinitiator packages we utilize. If I had to pick one of those LED lamps, typically the 365 nanometer is going to be closer to the photoinitiators that we use. Why is this lamp spectrum so important? Well, it's critical that the UV lamp and the UV adhesive have good overlap between the lamp output spectrum and the adhesive's photoinitiator. A good overlap will result in a good degree of cure and much faster cure rates. That photoinitiator is allowed to dissociate much more quickly, and that's going to generate faster, better cures. Here you can see the photoinitiator packages that we used overlapped with common lamp spectrum. In this case, it's actually the F or D typed iron-doped mercury lamp emission spectrum overlapped with typical photoinitiators utilized at EPO-TEK. You can see here an excellent overlap with many of the photoinitiators we use, and that the photoinitiators tend to be active from about the 250 up to about the 395, 400 range, but that the peak activation is in about the 300-ish nanometer range. For the free radical system, the graph below, you can see that the overlap for the photoinitiators is, well, less with the iron-doped mercury, but that emission spectrum overlap is not as critical in the free radical systems because they cure so much more quickly. And speaking of lamp spectrum output, it's additionally critically important when evaluating your lamp that you look to see if it has any filters. We commonly run into customers that don't even know they have filters in their lamp. And those filters can be cutting off critical UV wavelengths. You can see in the bottom right-hand corner that that's a 400 to 500 nanometer filter and is actually cutting out all of the critical UV wavelengths needed to polymerize a standard epoxy. That actually creates complete no cures, and we've actually had customers come to us and say no matter how long they illuminate our UV materials, they can't get any level of cure. It's commonly because they're filtering out many of the critical wavelengths needed to fully cure the material. Overall, we actually prefer no filter to be used. That said, the critical wavelengths for curing a UV system are going to be about 250 to about 400 nanometers. So making sure that those wavelengths are fully transmitted is going to be important to get a good quality of cure. Now onto the format. I discussed briefly how these lamps can break down into flood type and spot cure type, but here on the left you can see a picture of what the difference is going to be in terms of the illumination area. You can see the flood type has a very wide, uniform illumination area, great for larger cure areas or parts that you can't really get that spot cure down into. The spot cure has a very tight area of illumination. This is below, and you can see that the diameter is typically going to be around a 1/2 inch, and you definitely do not want to be curing large parts with these or moving your spot cure. You really want your entire bond line to be illuminated at once. The main difference between these two lamps is not just the area of cure, but the heat buildup that occurs within the lamp. The flood type lamps tend to get much hotter, between 70 and 80 plus Celsius, whereas the spot cure systems only get to about 30 Celsius. That additional heating of the flood cure systems can actually increase cure speeds, and we find to be typically beneficial. Output spectrum is not the only important factor when tailoring your lamp to your UV adhesive. Intensity is also critical. You need to get the right intensity to get a good quality and good depth of cure. We typically recommend about 100 milliwatts per centimeter squared. And I have many customers ask me, well, if it takes 1 minute or 2 minutes at 100 milliwatts per centimeter squared, what happens if we double or quadruple that? Can we reduce our cure times? And it's not that simple, unfortunately. What tends to happen is what we call skin over. You can see this on the bottom right-hand side, where the UV light comes in and cross-links the top layer of your bond and actually prevents the UV from getting deeper into your bond line. That's going to create a hard top with a liquid center. With a proper intensity, you can create great depth of cure, up to 1 millimeter, or I've even seen a couple of millimeters with lower intensity. In this case, larger bond lines require longer wavelengths. The higher wavelengths in the UV have less energy, and they're going to create better depth of cure. So how do you know you're getting the proper intensity at the bond line? We strongly suggest the use of a portable radiometer. This can be placed at the bond line. You can measure the intensity directly where the adhesive would see it. This is going to be much better than looking at the overall lamp intensity, because we're looking for what the actual adhesive is going to see over time. These intensities are typically tunable on the lamp itself, but some lamps that aren't adjustable, you can instead choose to back off that lamp and increase the distance to decrease the intensity. Now into the different types of lamps specifically, some of their pros and cons. The first here is the F-type or iron-doped mercury flood lamp. This is one of the most efficient, fastest curing lamps we see with most of our products. The lamp output is excellent in terms of its overlap with our photo initiator packages. Additionally, the flood type builds up excellent heat that creates great cure speeds and great cure quality. Now, these aren't as common in the industry and are a little more costly than some of the more standard UV lamps. The next on our list is a mercury spot cure. These are lower cost, very common. The light guides allow for great part accessibility, and the spectrum of output is typically quite good, quite a good overlap with our photo initiator packages. One of the main issues here is the lack of heat buildup and the small area of illumination. This can lead to generally longer cure times than, let's say, for example, your flood cure type lamps. Next, we have a pulsed mercury or pulsed xenon type lamp. These are very fast, very efficient curing lamps. In fact, the spectrum of output is very, very high overlap with all our photoinitiators. And this uses a pulsed type illumination that actually prevents skin over because it doesn't continuously hit the bond line with high intensity UV, but instead uses quick pulses that allow for a deeper cure. Now, these are probably one of the most rare lamps that I see in the industry. They're also quite costly, and it's a fixed lamp. And onto one of the most common lamps we see, the 365 LED flood lamp. They're low cost. The 365 nanometer is a very safe UV wavelength. And they're great for curing thicker films because of that higher wavelength, that lower energy wavelength. Some of the issues here is, as you can see from the graph on the top, the photoinitiators do overlap with the lamp output, but only slightly. Additionally, they don't build up as much heat as your standard mercury lamp. This, in some cases, can lead to substantially longer cure times. And we'll get into how some of the data of how that actually works. We've discussed the basics. Now for the actual data. Here you can see on the y-axis cure time, and on the x-axis a variety of EPO-TEK UV products. We've measured them with 4 different lamps, an LED, a spot cure mercury, a flood cure mercury, and a pulsed xenon lamp. Below you can see that with some systems, the lamp did not matter. Let's take the OG 198, 54, and 55. These systems are very fast curing, and any lamp can be used for a great quality of cure. That said, there were some instances, like the two on the right, the UJ1190 and the OG178, where you can see that the mercury spot cure and the LED cure took substantially longer to activate the systems. Here you can see that it is critically important for fast cure speeds to tailor your lamp to your adhesive. Here you can see another way of looking at that data. Here we actually coded the cure times, green being the fastest cures, yellow being relatively fast cures, the 2 stars, the orange, being the 3 to 5 minute, and the 1 star, the red, that's going to be your 5 to 10, and the other, the donut, your 0, that's going to be did not cure. You can see here consistently the iron-doped mercury lamps cured everything very well. In many cases, the 3 other lamps cured things very well. But there are some specific cases where, for example, the 365 nanometer LED just was not applicable, should not be used. The quality of cure and the time of cure is not what most people expect when looking for a UV system. So that concludes our UV section of the webinar. Now on to the brand new EPO-TEK UV hybrids. What is a UV hybrid? A UV hybrid is a UV tacking thermal post-cure required adhesive. This is a brand new technology that allows for tacking, alignment, position, or even flow control to occur in seconds of UV illumination. Those products can then be thermally post-cured, and with that thermal post-cure, their reliability is comparable to pure thermal cure systems. So the reliability is much more than any standard UV, whether it be UV cationic or UV free radical system. So the benefits and the drawbacks. The benefits is that what was previously a two-material solution can be simplified into a single material. Many customers, especially in optoelectronics, will use a UV material for tacking of a lens or prism or some type of optical component, and then will have to go back and add a secondary material for their long-term reliability bond. This hybrid system, or our hybrid systems, now allow for one material to be used. Additionally, they have very, very low shrinkage, great for high alignment, high precision optics. I've gotten feedback from customers that the shrinkage of these systems can be as low as 0.1 to 0.5%, even lower than your UV cationic systems. Additionally, the 8585 or damp heat resistance is comparable to thermal cure systems like our 353ND. The 353ND is well known for being able to go through autoclave, for example, in the medical industry, and these have comparable performance to that. Additionally, this can substantially increase throughputs on expensive alignment machines. One of the original development projects for the UV adhesives, the UV hybrid systems, was a machine that, multi-million-dollar machine, customer could only keep parts on it for 10 seconds maximum. 30-minute curing on this machine would have been just absolutely prohibitive. With the UV hybrids, they were able to go in and quickly illuminate, align their parts. They could then take them off their machine after 20 seconds, rack them up, and at the end of the day, put all of those parts into an oven and cure them together. They were able to get, I believe it was near 30 times the throughput that they previously had. Now, you can see here that this is designed as a process improvement. The performance is comparable with thermal cure systems. And if you can use a thermal cure system, you should. But if you find that UV tacking, UV alignment could be helpful, a UV hybrid can absolutely may be the material for you. Some of the drawbacks. Now, they must be thermally post-cured. This is not thermal post-cure optional. This is not a UV tacking and it will just continue curing. The thermal post-cure is required. And for thermal post-cure, we're typically talking about minimum 80 Celsius, preferably up to about 150 Celsius. And again, they have similar performance compared to thermal cure systems. This is not necessarily a performance improvement, but a process improvement. Now on to the data. On the left side, you see 353ND and OD2002. These are two industry standard materials that are very well known for their long-term reliability, damp heat resistance. Both of these are actually used in medical applications such as endoscopes, where thousands of autoclave cycles can be required. You can see the three on the right, the three columns on the right, are the three new hybrid systems that we're putting out. These are very comparable in terms of their pot life, their viscosity, their TG, cure times, all very comparable properties. The thing I really want to draw your attention to here is the bottom two rows, the die shear and the 8585. So the die shear here is done on a 2mm by 2mm silica die on gold-plated Kovar. You can see the 353ND and the OD2002 both started around 30 kilograms, and the hybrid systems also started about 30 kilograms. Now, we performed 85-85, so that's 85 Celsius, 85% RH, for 1 week on these samples, and then did die shear afterwards. You could see the 353ND dropped to about 6.7, the OD2002, 7.7 kilograms, and the three hybrids all stayed above that, 9.1, 7.7, and 8.6 kilograms after 85-85, showing that these truly are comparable performance to the industry standard thermal cure systems like 353ND and OD2002. Here you can see a marketing piece where some of this data was accumulated and condensed. So in case you'd like to continue to look at that data, it can be found on the brochure that should be connected to this webinar. So that's your general information on what hybrids are. Now, where can you use them? The hybrid systems were originally developed for the optoelectronics industry. You can imagine that aligning a lens with UV and then coming back for a long-term reliability bond would be a perfect application for these hybrid systems. And in fact, many of the first approvals of these systems were for fiber to lens alignment, for a fiber stub application where a fiber was being aligned to a lens block, for lens alignment in microscopes or other scopes, for example, sniper scopes. And lastly, for waveguides, where fibers will be placed into a waveguide, they have to be adhered. That cover glass comes on, and afterwards you need good, high quality pressure cooker resistance. That's absolutely the kind of application these hybrids are perfect for. The UV hybrids have also been used in the semiconductor industry for wafer-to-wafer bonding and alignment. For example, for a lens, wafer-style lens to a CMOS device, where the lens actually has to be aligned to the underlying CMOS device. Once that alignment is done, the UV will come and tack the material in place. Those can then be batched and thermally post-cured, where downstream they can be diced and singulated. Additionally, the medical industry has showed quite a bit of interest in the hybrid materials, specifically for endoscopes and laparoscopes. This was a common area where 353ND was used. We've had customers come to us asking for material where they want to stop the wicking of our material up to a certain point on the fiber. They want specifically 1 or 2 centimeters of wicking and then to have the material stop. That can absolutely be somewhere where the hybrid, the UV tacking, can be used for flow control. Additionally, we've had people come and ask us for a hearing aid sealing. This would be the material put on the outside edge of a hearing aid case. It would be UV initiated to tack that in place, thermally post-cured for the long-term reliability. Next, in general bonding and fixturing, we've seen quite a bit of interest in the hybrids. One of my personal favorites, the Pico projector. These would be a small projector that would be, for example, in phones one day. They needed a material to bond their magnets down to their MEMS carrier. These magnets are responsible for focusing the Pico projector. But without the UV tacking, when you put these into the oven, they would pull together based on magnetic strength. Here they were able to utilize the UV hybrid systems to tack those magnets down, then thermally post-cure it without the need for an extensive jig system. Additionally, in general bonding and fixturing, we've seen the hybrids used for multi-touch displays. This was piezo bonding onto the back of these multi-touch displays to actually target where the touches were happening. They had a variety depending on the size of this display, from about 20 to 40 of these piezos. They could place them quickly with UV and then cure them all together in heat. Onto the roadmap for our UV hybrid systems. So we've just recently completed a low CTE filled hybrid. Additionally, we have now a thermally conductive hybrid. These are both filled systems that are UV tackable, thermally post-curable. And in the future, we plan to develop an electrically conductive UV hybrid and room temperature curing versions of UV hybrids. These would be systems that could be UV initiated and then left on a shelf or in fact shipped to customers to allow to cure. We've actually have one of these in the pipeline, and the thing is, I will say they do take about 5 to 7 days for that thermal post-cure to occur. on to our conclusions. Jumping back to the UV epoxies, the fastest cures come from the best lamp optimization. So lamps that are tailored to the adhesive that you're using. Better overlap in terms of the lamp spectrum and photoinitiators lead to faster cures and greater quality of cure. Additionally, heat, such as that from a flood lamp, can produce faster cures. The takeaway for the UVs, a premium lamp for a premium product. That the better lamps are going to give you faster, better cures. And finally, thermally post-cures do measurably increase your degree of cure and your quality of cure. Finally, your UV hybrid summary. The UV hybrids are UV tacking, thermal post-cure required systems. Their performance is equal to, or in fact better, than compared thermal cure epoxies. They're specifically designed as a process improvement, not necessarily as a performance improvement. They have excellent performance, but the main benefit here is for processing. And they are ideal for alignment, positioning, flow control, and are great in precision optics. Thank you very much for your time and attention. I believe we're now going to be moving to some questions.
Okay, Brian, thanks so much for your insight into epoxy UV cure optimization and UV hybrids. Now we have some questions that have come in for you, but before we get started, we'd like to remind everyone if we don't get to your question, don't worry. We'll have an answer for you within 24 hours. The complete Q&A transcript, including answers we did not have time for, will be sent to all of our registered attendees and will be posted with the webinar when it goes into the on-demand mode. Okay, Brian, let's get to our first question. Is there a curing problem if I use my standard LED UV lamp with its wavelength of 365 nanometers?
That's a great question, one we run into all the time. It's actually fine to use a 365 nanometer LED lamp. The main concern with the LED lamps is the cure speed. As we talked about, the overlap between the photoinitiator packages we use and the lamp spectrum, there's only a small overlap of those the output to photoinitiator. In many cases, it's fine. In many cases, they'll work, but definitely something you want to be aware of, that you may need longer cure times than what's on the data sheet.
Okay, Brian, great answer. Here's another question. If heat is important, what do you suggest if my lamp doesn't generate a lot of heat?
Absolutely great question. Put it in an oven. The lamp doesn't necessarily have to generate the heat. You can take that part and after the UV illumination, put it into an oven, 80°C, 2 hours, and you're going to get a great quality of cure.
Okay, Brian, here's another question that came in. Can I use my own radiometer or do I have to use one from the lamp manufacturer?
Well, your radiometer is probably going to give you solid overall results in terms of your intensity, but it's best to use the one from the lamp manufacturer. The thing is the output spectrum that it covers. Some radiometers are not designed for a really wide range of lamp outputs, and you really want to make sure that the radiometer you have is going to actually measure the intensity of the lamp output.
Thanks, Brian. Next questioner asks, are there any plans to formulate thermally conductive hybrids?
There absolutely are. We in fact have 2 in the pipeline. If this is something you're interested in, please definitely drop us your email and contact information. We would be happy to follow up with you. If you find it, in fact, any of those that we talked about for the roadmap that you found interest in, please let us know. We're more than happy to have customers that we, evaluate those with.
Thank you, Brian. Here's another question. How long can you wait using hybrids between cures, UV, then the thermal cure?
One of my favorite questions so far. This one, because there's so much variability. The customers that I've seen do this in the past have gone entire shifts where they have UV illuminated parts right in the morning, and then all through an 8-hour shift been racking up parts, and not until the end of that shift did they move the entire rack of parts into the oven. That's absolutely fine. And in fact, I don't think you'd have any issues with even longer times than a shift. That said, it's not something we've looked into specifically, so you definitely want to do that evaluation with your specific parts and your processing.
And next up, what is the maximum depth of cure for most UV systems? And what is the maximum depth of cure for hybrids?
Well, that's going to be two very different questions for the UV systems as compared to the hybrid systems. For the UV systems, it's going to depend on the lamp output. As we talked about, short, high energy wavelengths will have lower depth of cure. They skin over more quickly. A little bit higher wavelength in that 365 nanometer can get deeper cures. Typically, though, on average, I would say anywhere from 0.5 millimeter to 1.5 millimeter, depending on your lamp thickness. Too much more than that, and you will get some liquid remaining at the bottom of your bond line. Now, the hybrids are a little bit different because the hybrids, you aren't actually going to get a fully hardened, cured system after just the UV illumination. You're going to get kind of a slightly softer, almost gummy bear-like material. It's going to be hard on the top, and it's going to hold its position, but it's going to be kind of a liquidous center. And because of that, it really doesn't matter what your bond line thickness is in that case, because the heat cure is what's doing most of the work. The UV is to just keep everything tacked up and in position.
Okay, Brian, we've got time for a few more. Let's take a look. How do I know if I have skin over a curing?
Well, skin over is either very obvious or a little tough to see, but there's a trick to it. When it's very obvious, it's because you see liquid just gushing out. You'll see a hard top, but when you push on it, liquid comes out. And that's your trick. That's how you determine. I usually like to tell people, have a witness sample next to their part, and with that witness sample, press it afterwards, 24 hours after, and see if you have any liquid coming out the sides. If you have a really liquid or like a lot of movement within that sample, you may have skin over, and you may want to double check your intensity at the bond line.
Okay, Brian, we've got time for one more. Let's take a look. As the hybrids are made for alignment and positioning, what level or percent shrinkage is expected after cure?
With the hybrids, extremely low. So here's your overall relative shrinkage, and this is just on average. Your acrylate, free radical acrylate systems, 10 to 15%. Your cationic UV epoxy, you're looking at about 1 to 5%. And your hybrids, now this depends on how you thermally cure them, especially. Very fast snap cures will lead to higher shrinkage, whereas stepped and ramped cures will lead to lower shrinkage. I've seen those get down to 0.1% up to about 1% shrinkage, substantially lower than either of the other UV systems. Okay, well, it looks like that's all the time we have for today. Once again, thank you so much for attending this webinar. We absolutely appreciate it. Once again, I am Brian Bruce for Epoxy Technology, and if you have any further questions, please send us those via email or through the webinar. We're more than happy to answer those, and if you have specific interest in any of these hybrids, we're more than happy to work with you on evaluating those. So please contact us. Thank you very much. Have a great day.
And thank you for being here with us today, Brian. That's about all the time we have, so we're going to have to wrap up this webinar right there. We'd like to let you know you'll be receiving an email from us with a link to the on-demand version of this presentation, a PDF of this PowerPoint, an FAQ document along with a Q&A transcript. Lastly, please take a moment to complete our survey, which will appear on your screen at the end of this webinar. Again, thank you for taking the time to learn more about epoxy UV cure optimization and UV hybrids. Take care, and we'll talk to you soon.